Here's a projectile motion problem that involves the following scenario. You have a ball here being launched off of a cliff, 30 degrees relative to the horizontal is the launch angle at 50 meters per second, and the cliff is stated to have this quantity that if you drop a ball from the cliff straight down, so it has nothing to do with the launch now, but if you just hold it here with your hand and let go and drop it straight down, it'll take 1.5 seconds to reach the ground. So those are sort of the conditions in the problem that are given. So you do have a launch condition, you have this information about how long it takes to drop a ball from the same position. And what they'd like to know in the problem is like how far does the ball land relative to the cliff after it's been launched. So you can sort of work at it this way. I said, well, what is the 1.5 seconds for? Well, what it is for actually so you can determine the height of the cliff, because you might imagine that the height of the cliff is going to have something to do with the range that this projectile can achieve, and indeed it does. So we can find the height of the cliff from this 1.5 second figure here. In particular, I'll do it this way. I'll say when the ball hits the ground, it's going to be at y is equal to 0, given that a start is some h, and I'll just pretend here that h is my physical distance, my height of the cliff there. That's my h right there. So it's going to hit the ground, given that a start at position h. Now I'm going to put a big 0 here for the v naught y, and that's because I'm considering the case in the facts of the problem where the ball is just dropped. So this has nothing to do with the launch condition. You're just holding here at rest and you're just dropping it. So v naught y is 0. And then of course you'll have the minus 1/2 g, and normally you put a delta t here, but you know how long it takes the ball to fall. It's 1.5 seconds squared, something like that. So this equation might look like I'm just pulling out of thin air, but I'm not. It's just equation 1 that we were sort of using in the class here, v naught y delta t plus 1/2 a delta t squared, something like that. Where again, v naught y is 0 because I'm considering the case where the ball was dropped. So the Brown equation has enough information in it to just go ahead and solve for h, and if you do that, you'll get a height of about 11 meters. So that's what I said at the start here, is the 1.5 drop time allows us to calculate how high the cliff is, period, 11 meters. So now that you have the 11 meters, you're in a good position now to figure out how long the ball, what the range of the ball is going to be. But the first thing you're going to need to calculate from that is this hang time, which is this quantity that we're sort of saying in our class is just extremely important. How long is this ball going to be in the air? Okay, that's the first thing you should calculate before you start even thinking about getting its range or its distance there. And you can get that using a sort of a similar analysis to this one here. Let's see how it turns out. Again, when the ball hits the ground, it would be at 0. It did start at a height h, which we now know is 11 meters, and it doesn't start with an initial y velocity of 0, but it has a y velocity of 50 times the sine of 30. So now where I'm getting that from is if you go back up here and look at this triangle, this component is v0y. Now if I look very carefully at the right triangle, it's the opposite side relative to this arrow right here, so that's going to involve the sine function. So that's v naught y. And of course we'll have a delta t in here, and you can also wrap this up by just putting the 1/2 g times delta t squared term in there. That's for an object in free fall. Again, equation out of thin air, no. This is y is equal to y0 plus v0y delta t plus 1/2 a delta t squared. It's equation 1, where I filled in v0y with the trig component there. So now what you have is you have a quadratic equation delta t, but you should be able to quickly find answers to quadratic equations either using your calculator or the quadratic formula. In either case here, the delta t that I'll get when I solve this quadratic here, I'll call it delta t sub ht, the hang time. That'll be the hang time of the ball. You get so many number of seconds for that. And I'll just let you to go ahead and do that calculation now. Once you have that time, then there's one last step in solving the problem to figure out what this range is going to be right here. So the way you calculate that range now is you go, well, okay, what is the x component of the ball's velocity? This initial velocity, that component right there, that's going to dictate how far horizontally the ball can ever travel. And now you know its travel time, which is going to correspond to the hang time of the ball. So it looks like the maximum range of this ball is going to be 0 plus v0x delta t, and normally there'd be a 1/2 at squared term here, but there's no acceleration along the x-axis for this problem here, so this is going to be a big fat 0 right here. Again, hope you don't think this equation out of thin air. This is just x equals 2 x0 plus v0 delta t plus 1/2 a delta t squared. So it's just the equation 1 that we've been using. And if you can just simplify it down a bit here, you will get that x is equal to, and v naught x is v0 times the cosine of 30 degrees. And then, of course, you have the hang time. You put in the delta t sub hang time right there, and that will give you the full range, knowing also that v naught is the launch v naught of the 50 meters per second. That's the 50 meters per second. So you can compute this whole thing, and that x that you get after you do that computation will be the horizontal range of the ball.